What's going on, guys? It's the Unhinged Engineer. I'm back today with a concept I think is super important to the technical kind of work that aerospace engineers do, but also is super simple. And it's not actually going to require any math or any weird derivations of anything. It's just something that I think is really important. You're taught it really on in your career and your education, but to really drive it home is to really understand it and bake it into almost all of the decisions that you're going to make over the course of designing aerospace vehicles and other kinds of platforms. So before I get into that, I'm the Unhinged Engineer. In case you can't tell, I make professional development content for aerospace engineers, people working on autonomous vehicles or AI in general. Basically, if you're trying to build cool, deep technology and you're kind of navigating your career as you go, like I am, then this is definitely the channel for you. So yeah, let's get into this super fundamental topic I really want to talk about today. And that topic is SWaP. So I would be surprised if anyone who's began their kind of engineering journey in any discipline, not just aerospace engineering, hasn't heard this before. But in case you haven't, it's an acronym that stands for size, weight, and power, right? And it serves to illustrate kind of two things, right? For one, just on its face here, these are what we care about. These are the qualities or characteristics of our system, our aerospace system, whether it's a drone or a satellite or even a driven robot, wheeled robot, whatever we're working on, that we care about. How big it is, how heavy it is, and how much power it consumes kind of in its normal operation. So on its face, it's just pointing out that these are very important qualities or characteristics of these systems as a whole. But the more kind of subliminal and in my opinion, deep-rooted foundational concept here is this concept of trade-offs. And I think that this is the point that really made me want to talk about this in video form, right? Because not only is it something that you kind of need to infer from this acronym, it's not explicitly stated here, but also I think this is where the magic really happens, and where when you talk to an aerospace engineer with years of experience, their understanding of this is what you can immediately tell sets them apart. Right? And so before we get into the specific concept of trade-offs with size, weight, and power, I want to just kind of affirm why I'm talking about aerospace here, right? Because as I'm sure anyone who's not studying aerospace is well aware, this is a very universal concept to engineering. This is important in mechanical, electrical, chemical, civil, whatever we're working on, right? But I think there's two fundamental things about aerospace engineering that make it particularly important and relevant. So the first one I want to talk about is kind of system level thinking. So this is the way I was taught in school when I studied aerospace. It's that, other fields like mechanical, electrical, some of the ones I mentioned, you're really studying like a field, an area of study. You're building up a knowledge base, right? That you are then applying to different applications of the system. And this is why, like, some of these degrees are much more versatile than you might assume an aerospace engineering degree is, right? So when you're learning about mechanical engineering, you're learning about mechanics and physics and dynamics and structural engineering, and that can be applied to lots and lots of different things. Now, contrast that with something like aerospace. Yes, we have to build up that foundational knowledge, obviously, but there's a shift that happens from those kinds of foundational knowledge base to a systems level overall view of types of platforms and types of systems like aircraft, spacecraft, boats, wheeled vehicles, robots, whatever we're working on in aerospace. So we shift our mindset from, okay, we're going to look at specific pieces of technical knowledge that we may need to apply in one way or another, and we shift to, we're looking at a specific type of vehicle or platform or systems level thinking that we need to analyze as a whole in order to be effective building it, right? And build it within the requirement set that usually have something to do with SWaP, as I'm sure you're well aware. And then second, speaking of those requirements, it's worth mentioning that, at least in my experience, building aerospace systems is a very resource constrained process, right? As compared to other fields. Now, again, I don't want to sound elitist here. Obviously, there are people who work in mechanical and civil or even biomedical who have encountered very resource constrained applications and projects who might be scoffing at me right now. But just to kind of illustrate this point, let's assume we're looking at the power consumption of a system in mechanical engineering and a system in aerospace engineering. So for the mechanical side, let's just talk about cars, right? If you're building a car, obviously you want the car to be fuel efficient. You don't want it to burn way more energy than it needs to, either in its gas or in its battery. If it's an EV, you want it to be fuel efficient. That's very important. But ultimately, how power efficient your system is comes down to just, something you can sell. Like, are you saying like, hey, I can run at this miles per gallon, or I have this length of charge time, distance of charge time, right? Which is something that we're trying to sell to people. Contrast that with aerospace, where if you're working on a drone and you're looking at how much power it consumes, that determines how far it can fly. And if you operate that drone without accounting for its power consumption, things start falling out of the sky and exploding, right? So this is just an example here of, hey, we're very, very resource constrained, and the tightness of these constraints really exacerbates these trade-offs I'm talking about here. Same thing goes for weight, right? With a car, we don't want a car that's heavier than it has to be. Right? We want it to be we want the structure to be as effective as possible for the minimum amount of material, either for cost or for how heavy it is, etc. Right? But with drones or with aircraft or with satellites, right, especially spacecraft here, each kilogram of material or weight in any capacity that we send up into space can be literally millions or at least hundreds of thousands of dollars, right? And so there's a consideration here to be made that's at a higher level. Every single gram on an aerospace vehicle has to advocate for itself and make sure that it needs to be there, or else it's going to get chopped, right? Which might be different from working on something like automobiles, okay? So these are the two aspects of aerospace engineering in particular that, I think, again, this is a super important concept for all fields of engineering, but make it particularly relevant to aerospace here. And then one last thing I want to talk about before getting to a specific example is SWaP-C. Right, so you may have heard it referred to as SWaP-C. The C stands for cost, as is probably unsurprising. And the reason I'm kind of leaving it out here is because cost is a very circumstantial thing that fluctuates a lot depending on what kind of project you're on, whether it's research or production level work, what kind of company you work for. There's a lot of factors that play into cost that kind of make it, extemporaneous to this technical conversation we're having about physical characteristics of our system. And the other reason I think kind of specifically with aerospace is, depending on what field you work in, cough, cough, defense, if that is the field you work in, cost may be more or less relevant, right? I'm not going to touch on the implications of that. That is for much more political channels than mine to decide. In any case, the point I'm trying to get at here is cost is another factor that we very obviously care about, but the degree to which you care about it will fluctuate a lot depending on the type of place you work or the type of work you're doing, and depending on what type of aerospace field you're working in, it might not be as relevant, right? And so this is overall the concept I want to talk about, but I want to use a pretty good example. It is an aerospace example to demonstrate this trade-offs kind of root concept I'm discussing here. Okay, to illustrate this point with trade-offs, really simply here, I'm going to draw a terrible picture of a drone. All right, let's just pretend this is a quad-rotor drone, and we're probably well familiar with how drones work, right? You've got this battery here, let's draw it in blue, battery, and the battery supplies power to these motors, which then spin these propellers and generate lift, right? We're all very familiar with how drones work, okay? Simple enough. And why am I using it here as an illustration of SWaP? Well, let's just talk about how in this simple example, we can immediately identify some very important trade-offs when making decisions about SWaP. So let's pretend, for argument's sake, we want our drone to fly further, right? Right now it has a range of 50 kilometers and we want it to be 80. The natural choice here is to get a bigger battery, right? So a bigger battery is the drone equivalent of a bigger fuel tank. Oops. More fuel, more power means further flight time, more range, right? Which is great, but now let's think about some considerations here. For one, the bigger battery is obviously bigger, which means more size, which depending on the form factor we're shipping these drones in, or how detectable we're comfortable with them being, or even the amount of noise they make, that can be a concern. There can also be a weight concern, right? So if we're making a bigger battery, it is more likely than not heavier. And so if it's heavier, then we need more power. So we have to make sure that this trade for getting more overall power capacity in this battery is not offset by how much heavier the battery is. And that kind of gets into the quality of the battery there, right? Also, these two are coupled because if we have a bigger battery, we probably need a bigger housing to store that battery, right? So bigger housing, more material, bigger vehicle, heavier, you get the idea, right? These are all coupled, and we might just catch ourselves kind of going into a whirlwind of saying, okay, we put this bigger battery on, now everything else about our power consumption has been hindered, right? So we need more power, our range didn't go up that much, and now we need an even bigger battery, which obviously this is circular logic. This is not what you want to do in the real world, but it's a very real kind of pothole that engineering teams can find themselves getting into, right? Now let's do a different example. Let's say, for argument's sake, we want the drone to be smaller, right? So let's say, let's just say we're trying to ship a bunch of them, and we want to store them all in these trucks. They gotta be smaller to store more. Or in a defense setting here, we want it to be less detectable, right? So smaller drone might mean smaller battery, which then means less power, which is a big uh-oh, right? Because now our range is significantly reduced, right? So smaller battery, smaller drone means smaller battery, means less power. But let's even get some of this cost in here, right? Now let's say it's a smaller frame on this drone. Well, is that frame just as durable as it was before, even with less material, right? Do we need more material? Like thicker kind of struts of this drone? That's going to be heavier. Do we need more expensive material, better material, like some kind of crazy carbon fiber that's way too much money, right? That's not cheap. These are all considerations of how saying, oh, we want the drone to be smaller, or oh, we want the drone to consume less power. It's not really that simple, because all these dynamics of SWaP and SWaP-C are interlinked, and how you change one affects how the others are changed, right? So as we're trying to turn these knobs in the directions we want, other knobs will start turning in ways we probably don't. And it's really, really important to account for this when we're engineering these systems, okay? So, yep, this is the super, super simple video I want to talk about today. There's no math, no numbers, but as you can probably tell, it's very, very technical. And as we're writing up requirements from the beginning, as we're doing testing throughout the development of our system, and then ultimately as we're measuring performance of the actual fielded platforms that we build, it's really, really important to keep these dynamics in mind, lest we fall into some of the rat holes that we see lots of very overly costly or inefficient systems fall into. So yeah, I hope you enjoyed this video. It is really, really good to be back in front of my whiteboard talking about some technical stuff and trying to lay out some ideas for you guys. Yeah, if you've been following the channel, if you've been a loyal viewer, thank you so much. I have been kind of running all over the place lately for reasons that I will hopefully be able to share very soon. So a little bit of a cliffhanger there. But yeah, thank you so much for watching, whether this is your 5th, 10th, 20th video of mine that you're watching. I make professional development content for engineers like myself. So if you're navigating this crazy thing we call careers in STEM and you're just looking for somebody else who's kind of learning as they go and trying to share those lessons to the best of their ability, then I really strongly believe that this is a channel for you. So please like, comment, and subscribe. Thank you so much for watching, and I will see you in the next episode.